Hello everyone, I'm Prakya Chen, Assistant Professor, Department of Mechanical Engineering, AIT Mangalore. Today I'm going to discuss about Module 2 of Fluid Mechanics. Topics include velocity potential function and properties of velocity potential function, stream function, and followed by properties of stream function. So let's first go for velocity potential function. So what is velocity potential function? It is defined as scalar function of space and time such that its negative derivative with respect to any direction gives the fluid velocity in that direction. It is represented by Greek letter phi. Mathematically, the velocity potential function is defined as phi equal to function of x comma y comma z. So we have three space coordinate x, y, z and time that is represented by small letter t. So this velocity potential function is a function of three space coordinates and time. So significance of this velocity potential function is negative derivative with respect to any direction gives fluid velocity in that direction. So we have velocity, the resultant velocity v. So components of velocities are u, v, w. So u is the velocity component in x direction, v is the velocity component in y direction, and w is the velocity component in z direction. So in order to get velocity component u in x direction, we have to take negative derivative of phi with respect to x, that is u equal to minus dou phi by dou x. Similarly, in order to get velocity component in y direction, we have to consider negative derivative of phi with respect to y. So that is v equal to minus dou phi by dou y. In order to get velocity component in z direction, that is w, that is equal to minus dou phi by dou z. So this phi is a function of three space coordinate x, y, z and time t. So mathematically it is represented as phi equal to f of x comma y comma z comma t. So if it is a steady flow, that is the properties are not going to change with respect to time, then phi is a function of x comma y comma z. So the continuity equation for an incompressible steady flow. So I already discussed about different types of flow, that is incompressible, compressible flow, rotational, irrotational flow, laminar and turbulent flow, so on. So what is incompressible flow? Incompressible flow means density remains constant, that is rho equal to constant. Steady flow means the properties are not going to change, like properties like pressure, velocity, those are not going to change with respect to time, that remains constant. So we already derived continuity equation in Cartesian coordinate, that is in xyz coordinate, as dou u by dou x plus dou v by dou y plus dou w divided by dou z equal to 0. Now we have values of u, v, w from definition of velocity potential function, as u equal to minus dou phi by dou x and v equal to minus dou phi by dou y and w equal to minus dou phi by dou z. So here in continuity equation we have terms u, v, w. So we can substitute u, v, w values from velocity potential function definition in that continuity equation. So we get dou divided by dou phi into minus dou phi by dou x plus dou divided by dou y into minus dou phi by dou y plus dou divided by dou z into minus dou phi by dou z equal to 0. So from property of mass, we can get simplified version of that expression as dou square phi divided by dou x square plus dou square phi divided by dou y square plus dou square phi divided by dou z square equal to 0. That is double differentiation. So take it as expression 1. So equation 1 is called Laplace equation, that is dou square phi divided by dou x square plus dou square phi divided by dou y square plus dou square phi divided by dou z square, that is equal to 0, is called Laplace equation. Now for two-dimensional case, now before going to two-dimensional case, we have to know what is one-dimensional flow, what is two-dimensional flow and what is three-dimensional flow. So in three-dimensional flow, we have to consider all velocity component in all directions, that is x, y, z direction. In two-dimensional flow, one velocity component is neglected. In one-dimensional flow, only one velocity component we are going to consider. So for a two-dimensional case, the Laplace equation reduces to dou square phi divided by dou x square plus dou square phi divided by dou y square equal to 0. We consider dou square phi divided by dou z square, that is equal to 0, because velocity component in z direction, that is w equal to 0. So we are going to get dou square phi divided by dou x square plus dou square phi divided by dou y square equal to 0. So if the value of phi that satisfies Laplace equation, then which will correspond to some case of fluid flow. If velocity potential is going to satisfy Laplace equation, that is dou square phi divided by dou x square plus dou square phi divided by dou y square plus dou square phi divided by dou z square equal to 0, then it will correspond to some case of flow that may be like rotational or irrotational flow. Now, properties of potential function. Before going to properties of potential function, we have to define rotational components. The rotational component. So what is the difference between rotational and irrotational flow? Rotational flow, in rotational flow, fluid element that is going to rotate with respect to its own axis during the flow. But in case of irrotational flow, the fluid element that is going to flow without rotating with respect to its axis. So rotational components are given by, that is Wz, that is in xy plane, that is equal to 1 by 2 into dou v by dou x minus dou u by dou y, and wy, that is in xz plane, equal to 1 by 2 dou u divided by dou z minus dou w divided by dou x, and wx, that is in yz plane, that is equal to 1 by 2 into dou w divided by dou y minus dou v by dou z. So we have values of u, v, w. We can substitute from velocity potential function u as minus dou phi by dou x, v as minus dou phi divided by dou y, w equal to minus dou phi divided by dou z. So we can substitute in rotational components. We get wz equal to 1 by 2 into dou by dou x into minus dou phi by dou y minus dou by dou y into minus dou phi by dou x, that is equal to 1 by 2 into minus dou square phi divided by dou x dou y plus dou square phi divided by dou y dou x. That is a simplified version. So wy equal to 1 by 2 into dou by dou z into minus dou phi by dou x minus dou by dou x into minus dou phi by dou z, that is equal to 1 by 2 into dou square minus dou square phi divided by dou z dou x plus dou square phi divided by dou x dou z. And for a yz plane, wx equal to 1 by 2 into dou by dou y into minus dou phi by dou z minus dou by dou z into minus dou phi by dou y. Simplified version is that is equal to 1 by 2 into minus dou square phi divided by dou y dou x z plus dou square phi divided by dou z dou y. So if phi is continuous, then from property of mass we have dou square phi divided by dou x dou y equal to dou square phi divided by dou y dou z dou x. Similarly, dou square phi divided by dou z dou x, that is equal to dou square phi divided by dou z dou x dou z, etc. So upon substitution of above property, we can get wz equal to wy equal to wx equal to 0. So because we can see here minus dou square phi divided by dou x dou y, that is equal to dou square phi dou y dou x. So minus and plus, that is going to cancel. So we are going to get wz equal to 0. And similarly wy and similarly wx. When rotational components are 0, the flow is called irrotational. So when rotational components, that is 0, that means the fluid element is not going to rotate with respect to its axis, then it is said to be irrotational flow. So hence the properties of potential function are, first one, very important one, if velocity potential phi exists, the flow should be irrotational. If phi has some finite value, then flow should be irrotational. If velocity potential phi satisfies Laplace equation, it represents possible steady incompressible irrotational flow. So this Laplace equation is applicable for steady state, that's the properties are not going to change. Then incompressible, density remains constant, and irrotational, where the rotational component is 0. So velocity potential phi satisfies Laplace equation, it represents the possible steady incompressible rotational flow, that is applicable for steady incompressible irrotational flow. So those are the two properties. Next, let's go for stream function. So what is stream function? It is defined as scalar function of space and time. Again, it's a scalar function of space and time compared to velocity potential function. So such that its partial derivative with respect to any direction gives the velocity component at right angles to that direction. So it is denoted by Greek letter xi and defined only for two-dimensional flow. Mathematically, for steady flow, it is defined as xi equal to function of x comma y. So it is defined for, this stream function is defined for only two direction, that is x and y, whereas velocity potential function, that is applicable for all three directions x, y, z. So again, this is scalar function of space and time, and it is applicable for only two-dimensional case, that is x and y. So significance of this is its partial derivative, that is dou by dou x or dou by dou y, with respect to any direction gives the velocity component at right angles to that direction. For example, if you want velocity component v, so in order to get v, we have to partially differentiate xi with respect to right angle direction, that is x. Dou xi divided by dou x equal to v. In order to get v, we have to partially differentiate xi with respect to y, that is y is the direction that is exactly right angle or 90 degree to y direction. So dou xi divided by dou y, that is equal to minus u. So it is defined for only two-dimensional case. You have to remember xi is a function of x comma y. So again dou xi divided by dou x, that means when you are going to partially differentiate xi with respect to x, then you can get velocity in y direction. If you are going to differentiate partially with respect to y, then you are going to end up with velocity component in x direction. So the continuity equation for two-dimensional flow is dou u by dou x plus dou v by dou y equal to 0. So that's the continuity equation. Again here, continuity equation is dou u by dou x plus dou v by dou y plus dou w divided by dou z. But here stream function is applicable for only two dimension, so we can neglect third term in continuity equation as well. So we get continuity equation as dou u by dou x plus dou v by dou y, that is equal to 0 for two-dimensional case. Now we have values of u and v from stream function, so we can substitute in continuity equation and get expression as dou by dou x in place of u, that is minus dou xi divided by dou y. So dou by dou x into minus dou xi divided by dou y plus dou by dou y into dou xi divided by dou x, because v equal to dou xi divided by dou x equal to 0. Or we can simplify, then we get minus dou square xi divided by dou x dou y plus dou square xi divided by dou y dou x equal to 0. Hence existence of xi means a possible case of fluid flow. Again, it may be rotational or irrotational. So the rotational components compared to previous derivation, that is velocity potential function, again we have to define velocity component in xyz direction. So the rotational component wz, that is in xy plane, is given by wz equal to 1 by 2 into dou v by dou x minus dou u by dou y. We are considering only velocity component in rotational component in z direction here. Then substituting the values of u, v, w, u and v in the above rotational component, we get wz equal to 1 by 2. In place of v, we have dou z divided by dou x. So 1 by 2 into dou by dou x into dou z divided by dou x minus dou by dou y into, in place of v u, we have dou minus dou z divided by dou y. So dou minus dou divided by dou y into minus dou z divided by dou y equal to 1 by 2 into dou square z divided by dou x square plus dou square z divided by dou y square. But for irrotational flow, wz should be equal to 0 in xy plane. Hence the above equation becomes as dou square phi divided by dou x square plus dou square z divided by dou y square equal to 0. So we have to cross multiply 1 by 2 to the other side, so then it becomes 0. So remaining term is dou square z divided by dou x square plus dou square z divided by dou y square equal to 0 for irrotational flow, that is a fluid is not going to rotate with respect to its axis. So which is a Laplace function for xi, similar to velocity potential function. This is a Laplace equation for stream function, that is dou square xi divided by dou x square plus dou square xi divided by dou y square equal to 0. This for only two-dimensional case. Next, the properties of stream function, that is xi, are if stream function xi exists, then it is a possible case of fluid flow which may be rotational or irrotational. Again, in case of velocity potential function, it was like if phi exists, then it should be a possible case of irrotational. But here it is not the case. If xi exists means it may be a case of rotational or irrotational depending on velocity component or rotational component value, like wz or wx or wy equal to 0. So if those components are equal to 0, then it is irrotational. If not, it is rotational. So next, second one, if stream function xi satisfies the Laplace equation, then it is a possible case of irrotational flow. So this is again similar to velocity potential function. If xi, that is a stream function, satisfies Laplace equation, that is dou square xi divided by dou x square plus dou square xi divided by dou y square equal to 0, then it is a possible case of irrotational flow. That is the fluid element is not going to rotate with about its axis. So these are the properties of stream function, two properties. So today we discussed about velocity potential function, stream function, its properties. So I'll come up with problems in next video. Thank you.